All right. Let's see. So we're going to define what impulse is. Impulse, we'll use the capital letter I for impulse, is our change in momentum. Well, actually, let's go back a page. I'm sorry. Skip something at the bottom here. So Newton's second law we know as F equals ma. But Newton didn't actually write the second law in that way. Instead, he wrote it in terms of momentum. And we know that momentum, which we've already defined, is equal to m times v. And so we can rewrite this Newton's second law if F is equal to m times A we define as delta v over delta t. Right, that's sort of our basic definition. Actually, back when we talked about this, we said that A was equal to dv dt. That's the first derivative of the velocity with respect to time. These are the same statements, basically. Delta v over delta t, dv dt. They're basically the same. When we're talking about derivatives, it's a rate of change in something. And notice here that this m delta v is equal to my delta p, because mv is momentum. And so Newton actually described our force as a change in momentum over a change in time. And this is a very important concept that we'll use. This is sort of the first part of this chapter in looking at impulse. If I have a change in momentum or an impulse that acts upon an object, then I can figure out what is the force. All right. I don't really use the word impulse that much in your problems, but if you're going on to take the MCAT or whatever, you might see it. So just know that impulse is a change in momentum. But again, as far as the tests and stuff, you're not really that concerned about it. But this impulse is equal to F times delta t. That goes back to our F is equal to delta p over delta t. And so it's just sort of reworking that equation. If I were to look at a plot of F versus t and say it looks like this, that F delta t is going to be the integral underneath the plot. And an integral is just the area under the plot. So this would be our impulse, which is equal to F, that's the y-axis, times delta t, which is the x-axis. It's the area under that curve. In fact, I have a student right now, or he's working on this project, where he measures the impulse for athletes when they do the broad jump and the vertical jump, because that's typically a way to measure their athleticism, how high they can jump, and then also how far out they can jump. And so what he's doing is he's measuring the impulse, he's plotting the force per time, measuring this impulse, and seeing if that's actually a better measure of athleticism. It's actually kind of a cool idea. It was his idea, but Alex was going around. He's awesome, isn't he? So he's looking at football players and measuring the impulse for those football players and seeing how that correlates with how good a football player they are. And there are measures of that for the vertical and the broad jumps, but never for collision, at least not as far as we know. All right, let's look at a collision problem, because this idea that our force is related to the change in momentum is pretty important for determining the force in collisions. Let's see, when I was a kid, we had this 1964 Fleet-side Ford pickup truck. You ever seen a 64 Ford truck? No? My dad had it. He got it as a young man, and then he gave it to my brother. But sort of when I was a teen, it was sort of at the end of its life. And we used it around the house just to do chores, like to move limbs or whatever, to carry trash away. But the truck, as it got older, it didn't have any brakes. And it was an old truck, so we didn't even bother fixing it. But whenever we wanted to go out in the truck, we would always, if we wanted to stop, we would gear the truck down as much as we could, like go from third to second to first. And that slows down the vehicle without brakes. And then what do you think we'd do? We'd what? No, we didn't have an emergency brake. No emergency. We would just find something to run into. So we had this big tree out in front of the house that we always parked it in front of, and because it was a big tree and we just run right into it. But we would be going slowly because we would gear it down and go really slowly. So we can figure out the forces that are involved. If I take a truck, for example, that's going from a certain speed and then to rest, or maybe it bounces off of whatever you're working with, you can figure out the force that actually causes that change in speed. So let's consider this problem. Let's say that we have a car. It has a mass of 1,000 kilograms, smallish car, and it collides into a wall. And so here's a picture. The car is initially traveling at minus 10 meters per second. It hits the wall, and then it rebounds just a little bit. Not at the same speed, at a slower speed, but it rebounds just a little bit. And I want to figure out what is the force that causes this change in motion for the car. Well, I know that my impulse is my change in momentum, and that's equal to mvf final minus mv initial. And notice these are vector quantities, so that's sort of the tricky part on these impulse problems, is making sure that you include the direction for the speeds. This is going to be equal to F times delta t. So if I want to figure out my force, it's going to be that change in momentum, m times vf minus vi. I just pulled out that m, divided by delta t. This goes back to Newton's original idea that F is equal to delta p over delta t. All right, this is the same thing. This is my change in momentum. This is my change in time. So, in this context, if I want to calculate this, I say that the force is equal to 1,000 kilograms. The final speed, which is plus 2 meters per second, minus the initial speed, which is minus 10 meters per second, and then divide that by the time. The collision, it says, occurs in 0.1 seconds. Usually these collisions do occur in a small amount of time, so that's equal to 0.1 seconds. And then we can figure out the force. That's going to be equal to 12,000, because 2 minus negative 10, that's 2 plus 10, that's 12, times 1,000, divided by 0.1. So 12,000 kilogram meters per second, divided by 0.1 seconds, that's equal to 120,000 newtons. So a common way for us to lower this force, or to decrease the force, this comes up in your OpenStax, by the way. I think there's a question there. To decrease the force, you can do two things. One, you can change the delta V. If you make that smaller, if I make delta V smaller, that is, I just drive slower, for example, then that'll make my change in speed a lot smaller. That's often not very practical to change, like say, for example, in a car accident, because that's set by the driver. I mean, there are speed limits and all that are meant to control sort of how fast you drive. But that is one way to decrease the force that acts on the vehicle and on the driver inside. What's another way to change the force? I can decrease delta V. What's something else that I can do? Well, F is delta P over delta T. If I change V, the change in speed, then that changes the change in momentum. What else can I change here? I can increase the time. And that's often what car companies will do, is they want to, if I have a collision between a car and, say, another object, a tree, for example, then I can increase the time. And so you're thinking, how does the car company increase the time in a collision? Well, listen, that old truck that we had, the bumper on that old 64 Ford was made out of what, you think? It was steel, right? That's why we ran into a tree, because it didn't do anything with the truck. The Ford tree got all banged up, but the truck, nothing happened to it. So even if you're going at a pretty slow speed, it would be a considerable lurch for you to run into this tree, as you might imagine. But a modern car, the bumper is made out of what? Yeah, foam and plastic, all sorts of stuff that crumples up when it collides with something. And then that actually causes this T, this time, to increase. And so we can get an increase in T by design of the bumper. I think it's called like a crunch zone, if I'm not mistaken. I'm not a designer, but I think that's what they call it, a crunch zone. Another way that they do this, and I don't think they really do this with cars so much, but you ever watch those races where they, I forget what they're called, funny cars or something? What are they called? They're really, really fast. Anyway, these cars, they race, and when they crash, man, you see stuff coming all off of those cars. You know what I'm talking about? The wheels are popping off, the whole body is popping off the car. When you have that, that takes momentum away from the car as well and sends it off into places that it doesn't really matter. But anyway, to decrease the force, you can either change the change in speed or you can increase the time. All right. Let's watch a little video. This is a video of the Honda facility where they... All right, so we want to figure out what is the force that caused the dummy to change his speed the way that he did. So just a couple things we'll need to know. First of all, the initial speed of the dummy. He was initially at rest, 0 meters per second. We need to know his final speed. We'll come back to that and we'll talk about it. And then we also need to know the time that he uses, that is necessary for him to go through that change in speed, the delta t. And then finally, we need to know the mass. All right, so we'll assume that the dummy will actually come up to the speed of the car. But the car hits him, and then they both travel along at the same speed. So that dummy goes from 0 meters per second to 40 kilometers per hour in just a very short duration of time. 40 kilometers per hour, that's equal to about 10 meters per second. You can do that conversion if you like. It's approximately 10 meters per second. The delta t we don't really know, but that's part of what they measure there. Actually, you know the lab where you did the thing spinning and then you also did the balls where you did the video analysis? That's very much what they do. That's why they put those black and white discs on the side of the dummy's head. Those just help them to mark out where the dummy's head goes, and then they can measure the change in speed for the head and then also measure the forces that are acting on particular parts of the dummy. But the delta t, we'll just have to estimate. I don't really know what the delta t is, but let's say that it's about 1/10 of a second. That's probably about right. It might be less than that even. Less than 1/10 of a second or 100 milliseconds. And then the mass is probably going to be pretty typical for a person. I'm going to say about 70 kilograms. That's about 700 newtons, about, I don't know, 170 pounds or so, 160 pounds. So given that, we can figure out the force. Remember, our force is delta P over delta T. That's going to be M times delta V over delta T. M times 10 meters per second minus 0 meters per second divided by my time, which is 0.1 seconds. And let's see, this mass here is 70 kilograms. And so for what is a fairly conservative estimate of the time, it's probably actually less than 100 milliseconds. We get 7,000 newtons of force that's acting on the knee of this dummy, which is sort of where the car hits the dummy, acting on that knee just within a very short amount of time. That's like having, well, 10 people, 10 sort of normal-sized people sit on top of your knee. All right, let's do this quick test. You'll definitely have some questions like this on the upcoming test, which is not next week, but the next week, and will consist of chapters 5, 6, and 7. Most or all of 7, probably all of it. A couple ways you can do this, but I'll let y'all play with it, and then I'll show you. All right, let's wrap up here in about 15 seconds. I'll stop at 225. 225. Okay, first of all, let's just draw a picture. Let's think about what we got here. We got a football. It's traveling along at 10 meters per second. And then you got a guy over here, catches it, and in 0.04 seconds, that football comes to rest. So it initially has a speed of 10 meters per second. It says it's thrown to the east, which is going to be positive 10 meters per second. And here, the speed is equal to 0. So his initial speed is 10, his final speed is 0. And then I want to know the magnitude of the acceleration. Look, a real easy way to do this is to recognize that A is equal to delta V over delta T. That comes from this equation that V is equal to V naught plus AT. And then solve for A. Works out to be V over T. And I'm looking for the magnitude, so I'm just going to sort of forget about the signs. But the change in speed is going to be going from 0 to 10, or 10 to 0. So I have 10 meters per second divided by 0.04 seconds. So that's probably the easiest way, which gives me 250, which is the answer. All right. Actually, the sign for the acceleration is going to be negative because the object is traveling in this direction, in the positive direction, and it's slowing down, so the acceleration is going to be opposite the direction of the velocity. However, let's say that I also wanted to approach this from a momentum standpoint. I could say that F is equal to delta P over delta T, and I can figure out the force that is acted on the football. That's going to be a half a kilogram, 0.5 kilograms, times my change in speed. So this is mvf minus vi divided by delta t. Vf is 0 minus vi, which is 10, divided by t, which is 0.04, and you're going to get 125 newtons. So 125 newtons is the force that we have acting on this object. And then if I wanted to find the acceleration, that's going to be F over m, which is 125 over a half kilogram, which will give us this 250. Okay? But you need to be prepared to be able to do this sort of thing if I have an object that changes speed or changes its velocity, to be able to calculate what is the force that's acting on that. That's sort of one class of problem that you'll have on the next test as it regards to momentum. There are some others, we'll practice some soon, but there are some others also in the workbook. Let's do a few quicker questions actually. Actually, no, I'm sorry, never mind. I'm gonna show you conservation first before we move on to that. I'm sorry, flip back. Okay, so now we're looking at conservation of momentum. So you have this impulse and momentum, calculating the force when I have an object that is involved in a change in a velocity that collides with some other object. Conservation of momentum will occur when I have two objects that collide and then they bounce off of one another. And I want to figure out what is the initial or final speeds of either one of those objects. So the conservation of momentum says that my initial momentum is equal to the final momentum. That is to say that Pi is equal to Pf. Remember, these are vector quantities, and if I have particles in a system, when I say that, I mean I have two or more particles. Remember we talked about earlier how if I have a system of particles, and say I have two particles that are going in opposite directions, I have two other particles that are going in opposite directions so that they all have equal and opposite momenta, that I can add up the momentum of each individual particle, and that the net momentum, in this case, would be equal to 0 because it's a vector quantity. And so the momentum of this object and the momentum of this object, if I consider it as an entire system, then they would all cancel out with one another. This is a vector quantity. So let's do this problem. This is going to be very similar to what you'll have in your test. And this is similar, too, to what you have on your OpenStax assignment. You'll find some extra practice there for these, doing that. So let's say that I have these two particles. I have M1, which is 3 kilograms. M2 is 4. So 3 kilograms, 4 kilograms. And then I have their initial speeds given. V1I is 1 meter per second. And V2I is minus 2 meters per second. And then after they collide, they hit one another. V1F is minus 5 meters per second. And I want to know what is the speed of this particle. And so what I do is I begin with my conservation of momentum. I say that Pi is equal to Pf. That is M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. All right, that is the conservation of momentum all written out. And as we have two particles for each initial and final, and so that's why I have a term here and I have a term here. Now, I am looking for V2F. I want to know what is this value, the final speed of that second particle, but that's the only unknown that I have. So I can put in the values for the other quantities and solve for V2F. So M1 is 3 kilograms and 1 meter per second. M2 is 5 kilograms, or excuse me, 4 kilograms. And V2I was negative 2 meters per second. Very careful to watch your signs on these. A lot of students will miss this problem on the test because they get the signs wrong. So make sure that you read carefully through the problem. If there's a diagram, or if there's not a diagram, draw a picture and just label very clearly what the signs and directions are for the velocities. M1 again is 3 kilograms. The final speed was minus 5 meters per second. Plus M2, which again is 4 kilograms. And then V2F, which is what I want to know. So this is 3 minus 8, negative 5, plus 15 equals 4 V2F. And so V2F is 10 divided by 4, which is 2.5 meters per second. All right. It's a pretty powerful tool that when I have two objects collide, that I can figure out the velocity of those colliding objects. In fact, y'all might have seen this in chemistry, or let's see, y'all had Chem 106, is that right? Yeah, so when you're dealing with gas particles, this is often the way that you develop the classical idea of thermodynamics, that you treat gas particles as particles that collide with one another, and then you can develop this idea about how they behave thermodynamically. It all starts with this, with a conservation of momentum. It also deals with conservation of energy too, which we'll talk about soon. Okay, so that's a good example of the test question you'll see. Yeah, Gavin? 2.5. Oh, because I have 15 minus 5 over here, so that's going to be 10 divided by 4 is V2F. And 10 divided by 4 is 2.5. I did that right? Yeah, I divide both sides by 4. I get 10 over here, divide both sides by 4, That's 2.5. Okay. Good example of a test question. And again, on the OpenStax assignment that I gave you this morning, that's due next week on Wednesday, I think, you'll see some that are very similar to this, and you'll see some of these on the test as well. Practice it a little bit. If it's a little foreign to you now, with a little bit of practice, it won't be anymore. Trust me. It's a lot easier than, say, what we saw in chapters 3 and 4. Oh, let's see, what was this one? Oh, yeah, so let's do some clicker questions first, and then we'll come back to this. So an open cart rolls along a frictionless track while it's raining. As it rolls, what happens to the speed of the cart as the rain collects it? And you assume that rain falls vertically into the box. You want to think about this, that PI is equal to PF, that the total momentum of this system will be conserved, will always remain the same. And so as I put more mass into the cart, what's going to happen to the cart in order to keep the momentum to be the same? All right, so let's stop at 110. Okay, good. C is the right answer. My momentum has to remain constant. But as mass drops into the cart, the mass is going to go up. Right, the cart is going to get more massive as the rainfall drops into it. And so therefore, for P to remain constant, V has to decrease. So C is the right here. We've already seen this question. I'm going to skip it. And we've seen this one too. Remember, this was just that if it has a total momentum of 0, that does not necessarily mean that the particles are not moving. All right, let's stop at 42. 42. Good job. B is right. That if they have the same momentum, that does not necessarily mean that they have the same kinetic energy, because momentum is m times v, but kinetic energy is 1/2 mv squared. And so I can have an object that has more mass, but it has the same momentum. It'll have, how does that work? If it has a bigger mass, it's going to have a lower kinetic energy. We'll get into this. It's because of the quadratic term, that the speed affects the kinetic energy more than the mass does. Oh, y'all did well? So this isn't really a joke. It's just sort of a funny story. I used to be a bartender when I was in college. I waited tables, but I also attended bar too at this little place, Harvey's. Anybody from Mississippi? No, I didn't think so. Anyway, it was in Mississippi, and one day this guy comes in, and I think his car was broken down or something, but he had some jumper cables. He walked in, he had some jumper cables just sort of hanging over his shoulder, and he comes in and he's like, "Hey man, I need some help." I was like, "You can come in, but don't try to start anything." Gives me a jumper cables to start a car. That was a joke. It wasn't a real story. I did 10 bar, but that didn't happen. Okay, let's try this. All right, let's stop at 115. 115, just guess if you don't know. 115. Okay, good. C is the right answer. It seems misleading that I should have a bigger change in momentum for the pebble, right? Because you think this force is going to make the pebble move more quickly. But let's think about what is momentum in terms of force and time. So a change in momentum is equal to a force times a delta t. That's our impulse, right? But notice here that the force is 200 newtons for the pebble and for the boulder. Also, the time is the same. Where's the time given? Well, it's the same amount of time on both of them. So our force is the same, and our time is the same, so our delta p is going to be the same for both. Our change in momentum for both the boulder and the little stone are going to be the same. Let's try this one. Free to ask your neighbor if you're uncertain, or please do ask your neighbor. All right, let's stop at 43 or 45. Y'all don't look very excited to be here today. Are you not? Is it because it's fall break tomorrow? Is that why? But look at you, like almost everybody is here. It's because y'all are awesome. Y'all are like the best students at Nichols. Do y'all know this? Have I told you this before? That you're the best student at Nichols? You, in particular. No, like, statistically, this class is really awesome. Okay, okay, good. B is right. Yeah, the boulder is going to encounter a smaller change in velocity just because it's bigger. It encounters the same change in momentum, but because its mass is bigger, its change in velocity will be smaller. All right, a small car and a large truck collide head-on and stick together. Oh, which one has the larger momentum change? Actually, I want to skip this one, okay? I'm just going to stop it. Everybody just put in A for now, and I'll give you credit for it. But we're going to wait till we get to inelastic collisions. All right, everybody put A. Don't mark A as the right answer. It may or may not be the right answer. Some of you just want to be particular about things, don't you? All right, that's okay, I understand. Okay, let's watch this one video at the end and we'll work through another example. The other day.